So we started, well, in lecture 7, which was before lecture 6, we started looking at group theory. We looked at the definitions of a group. We looked at how they relate to symmetries. And we saw some examples of discrete groups. So the topic of today instead is to look at what is called continuous groups. Or Lie groups. So we saw that many of the examples we had were not discrete symmetries, but they were continuous symmetries. So for example, translations and rotations, when you can do them by an arbitrary amount, that's not a discrete symmetry, it's a continuous symmetry, because you can translate by any real amount, you can rotate by any real angle in general. Of course, we can restrict rotations and translations to discrete values, but translations and rotations by arbitrary values will keep being a continuous group. So in general, for any continuous transformation, so we can call it T, we can do that transformation, we can do it a multiple of times, or we can do it a fraction of the times, or we can even do it we can multiply it by, we can do it any real number of times. So we can take any real power of this transformation. And we will call that T to the theta, where theta is a real number. So for example, taking theta equal to 0 will be the identity transformation because we're not doing anything. Taking theta to be pi is, if T is a translation by some fixed length L, then T to the pi is making that translation, making a translation by pi times that length. So for example, just taking that as the example, if we let TL is translation by L, so that would mean that if we apply TL on a coordinate x, that would be equal to x plus L. Then TL to the theta acting on x would be just translating by theta L. So in other words, in this case, T theta L would be equal to T to the TL to the theta. So in the case of discrete groups, we discussed that there were generators of the group, and they were all finite generators. So any group element could be written as some combination of the group generators. So in the continuous case, this is no longer the case. So instead of discrete generators, GI, that we had in the discrete case, we introduce a set of infinitesimal generators. In general, I'm going to call them JI. That formally, we should be able to write any element that is at least close to the identity as the exponential of some sum over I, and then theta I ji, where the thetas here are real numbers. So using the summation convention in the future, I will just write this theta I ji. So this so far is just a formal definition, and we're going to see where this leads us when we have a bit more hands-on examples. So to look again at an example, we can look at the group of translations and rotations in 2 dimensions. For 2D translations and rotations, we need 3 generators because we can rotate in one direction, we rotate in one plane, and we can translate in 2 directions. We can translate in the x direction, and we can translate in the y direction. So we need 3 generators. We take them to be px, py, and l. So px is the generator of translations in x. Py is the generator of translations in y, and L is the generator of rotations. Now, I call them P and L because, as we saw when we were discussing symmetries in the Hamiltonian case, the generator of translations was momentum. That's why I called it P. And the generators of rotations was the angular momentum, and that is why I call it L, because we will be able to make the connection later on when we look at Hamiltonian mechanics. So typically, a translation here by some vector L would be TL. I would write that as e to the L and then the scalar product with P, where P is just a 2-dimensional vector with having the generators. So this would be just e to the Lx Px plus Ly Py, and a rotation by some angle theta that would be written as r theta, which would be e to the theta L. And then we can, of course, make combinations of those to make combined translation and rotation.
Can I ask a question?
Yeah, sure.
Why do you use e to the power? As far as I remember, e was the identity.
No, so e here is just the natural base of the, so it's the exponential function.
All right.
So it's not the identity here. The identity I will write in continuous groups. I will write it 1.
All
so
right.
there are some different notations.
Why are we using the exponential?
I mean, so far this is just formal, the formal definition, but we will see that later on when we go to, for example, matrix groups, it's going to be actually the matrix exponential.
All right, all right.
So far I've just done things formally, and I'm going to expand things formally. We don't really know what these objects are, but yet, but we will see how it all works together when we expand things formally. So the main thing here is that for small transformations, I'm going to expand this as 1 plus whatever is up here, and then high order terms in thetas. Yeah, actually, that was the next thing I was going to do. So, so formally, we have not said what type of objects these J's and these and these transformations are. They are just transformations, and we don't really know what the j's are. But formally, if we have this exponential function, then e to the theta I ji, that would be approximated by 1 plus theta I ji, right? And then higher order terms in theta. So theta squared. So what we can see here in particular is that to leading order, so if we have a transformation that is close to identity, these things are always going to add. So they're going to form a vector space. So we can look at these generators as forming the basis of a vector space. So the generators form the basis of a vector space. If one wants to be a bit more theoretical about it, so continuous groups, well, you're going to be able to describe these continuous groups in terms of a number of continuous parameters. So that's a space, as we have seen it already in the first few lectures. And these generators are actually going to be a basis for the tangent space of the group. So that being said, now for an abelian group, we know that since by definition in an abelian group all the group elements commute with each other, we know that e to the theta 1 j1 and e to the theta 2 j2, since the group's elements commute, this would be e to the theta 2 j2, which is also equal to e to the theta 1 j1. So we have a commutative group in the abelian case by definition. And we can also write this as e to the theta 1 j1 plus theta 2 j2. However, many groups are not abelian. In particular, many of the groups we will look at will not be abelian. So what I want to look at now is the relationship between this left-hand side and this right-hand side. So what I can do is to make this formal expansion, and I'm going to make it to second order now. So if I take e to the theta, I used theta and phi in the lecture notes, so let me do that here also. If I take these two and I expand them, and I do it to second order in theta and phi, so I'm going to get something like what follows. So this is again just doing this formally, and then keeping in mind that the generators ji do not necessarily commute with each other. So the order in which I write them is going to be important. The thetas are just real numbers, so where I put them is not going to be as important. So if I do this, I end up with a 1, which is just 1 times 1. And then I have this linear combination of theta j1 plus phi j2, as I thought I would have to linear order, because this is a vector space here, and I can add vectors in that space. However, to second order, we're going to have something slightly different. So we're going to have 1 over 2, and I'm going to have theta squared j1 squared, and that comes just from the second order term in the expansion here of the first factor. I'm going to have phi squared times j2 squared, which comes instead from this factor. But then I'm going to have 2 more terms, and those terms are going to be, both are going to be theta phi j1 J2. And since I have 2 of them, I'm going to get a factor of 2 in front. So we can see that this is not the same thing as if I would reverse the order here. What would happen if I reverse the order is that, well, this term, well, actually the first terms, both the 0th order term, which is just the identity, and the 1st order term, which is just linear in everything, they are both going to be the same, because if I change J1 for J2 and theta for phi, I get the same thing back. The same thing is true for those two terms, but it's not true for those two terms, because instead of getting J1 times J2, I will have J2 times J1 instead. So this will be here, if I here put e to the phi J2, e to the theta J1, I'm going to get exactly the same thing, apart from here where I will have 2 phi theta J2 J1. So actually, if I look at this, so what I can do is that I wanted to see what the relation was here between this and this. So in order to see that relation, I can also multiply by the inverse of this from the right here, and to see what I get. In the abelian case, I would get 1. So what I want to look at now is something of the following form. So e to the theta J1, e to the phi J2. So that was just this. And then the inverse of this. So that's e to the minus theta J1, e to the minus phi J2. And then when I do this, this same thing, I keep all terms up to 2nd order in theta and phi. I will get 1. The linear terms are going to cancel between them, because we saw that the linear terms in those two are going to be the same. Which means that we're only going to be left with the 2nd order term. And since those terms are the same, they're not going to appear. But what is going to appear is phi times theta multiplied by J1, J2 minus J2, J1 plus higher order terms in theta and phi. Now, since this left-hand side is an element of the group, because it's a multiplication of elements in the group, then this right-hand side must also be an element of the group. And the 1st order here, or the leading order contribution, is therefore a part of this vector space formed by these generators. And I should say that also that this vector space is called the Lie algebra of the group. So this thing here, which is formally expressed as J1, J2 minus J2, J1, this must be an element of the Lie algebra. And I'm going to denote it as J1, J2 commutator. And we're going to see when we look at matrix groups that this is actually going to be a matrix commutator in the case of matrix groups. We're also going to see that if you remember what we talked about when we talked about symmetries in the Hamiltonian mechanics, we had the Poisson bracket, and we had the Poisson bracket between rotations, between the generators of rotations, which were the angular momenta. And we're going to see that the if we look here at the translations and rotations that we had as an example, we had the momenta and we had the angular momentum here. And this Lie algebra commutator is just going to be the Poisson bracket.
Can I ask a question?
Sure.
Will this be this commutator J1, J2? Will this be a basis vector in Lie algebra, like a tangent?
I mean, it might not be a basis vector. I mean, generally, your basis vectors are the Ji. So in general, you will be able to express this as some constant. I mean, this will be some constants that will depend on 1 and 2, and then with an I, and then times Ji, because since it is an element in the Lie algebra, it must be expressible as a linear combination of the generators of the Lie algebra.
Because I wonder, why do we call it algebra? Like, why? What is the reason for that?
Because it has this this commutator. So it's a vector space that additionally has a binary operation,
All right.
which is this operation, which is this commutator that maps back to the algebra.
All right, I understand. Thank you.
Okay. So we have, I mean, this is a binary antisymmetric map, because you can also see that it's antisymmetric, because if I change the rows of 1 and 2, then I change the sign here. And these F, so in general, of course, you would have J should be equal to some Fij jk. And these F's are called the structure constants. So let's actually look at the more concrete realization of this. So we looked at translations, and I mean, translations are abelian. So that means that since everything commutes, these commutators for just translations are going to vanish. So in the abelian case, all of these commutators map to 0 because it's a commutative group. So what I want to look at instead is rotations in 3 dimensions as a Lie group. So how do we describe a general rotation? Well, we would have some vector, some unit vector n that we want to rotate around. And so we can describe our rotation by giving one unit vector, which we rotate around, but also giving an angle, theta, with which we rotate. So if we took a vector here, if we take this vector v, that under rotations would rotate some angle theta and would map to what we will call r and theta v. So that's what rotations do to different vectors. So our rotation, in order to describe a general rotation, we give one unit vector, which is giving a vector on the sphere, and we give one angle with which we rotate around that vector. So the question is now, how do we express this r and theta and its action on v? So if I want to do that, if I just want to, so what's going to happen is that when we do a rotation, what we're actually doing here, right, is we are taking the projection of v onto this unit vector, and the rotation is going to preserve that. Whereas the component that is orthogonal to n is going to rotate by some angle theta. So in order to do that, we need to know, first of all, what is the component of v in the direction of n, and that's going to be, so if we just write down v, that's going to be n multiplied by the inner product between n and v, because since n was assumed to be a unit vector. And then the second term is going to be actually minus n cross v. So those are you can use the back-cab rule for this cross product to see that this is actually the case. So what's going to happen now is, what I want to do is that I want to keep this component as it is, while I want to rotate this component by an angle theta. So the way to do that is to keep this component as it is, and when I rotate by theta, I get a cosine of theta times the same thing that was here, n cross v. And then I need to rotate this into a vector which is orthogonal both to n and to n cross v. And that vector is just n cross v. And the component that I will have in that direction is proportional to sine theta. It's going to be sine theta n cross v. So this is the general rotation by an angle theta. Comparing to what we did before for the general case, when we look at rotations by small angles, so for small angles, you see that if we look at the first two terms, this term is, the cosine is 1 plus something that's order theta squared. So when I just do things to linear order, oops, sorry, there should be a v here because we're acting on v. So Rn theta acting on v, to linear order, it's going to be this same thing for the zeroth order contribution. So that's just v. But what's going to give me the linear contribution is this sine. So the sine to linear order is equal to its argument. So it's going to be plus theta n cross v. So if I want to look at this commutator between rotations, so I'm going to take now 3 generators of rotation. So the 3 generators are going to be L1, L2, and L3. And they generate rotations around their respective axes. So Li generates rotations about EI. So this means then that that e to the theta L1, that's going to be given by, well, acting on V, that's going to be given by V plus theta E1 cross V plus higher order terms in theta. I'm also going to write this as r theta 1 acting on v. Just as a shorthand. So what do we do with this? Well, we wanted to have the commutator here between rotations. So we're going to look at something like this. So let's do that. So if we do that, what we want to write down is r1 theta, r2 phi, r1 minus theta, r2 minus phi. And we want to know its action on v. And if we do that, and we keep all the terms to the correct order, we're going to find out that this is actually v plus theta phi E3 cross V plus higher order terms. So what this means is that this is actually a rotation around the third direction. So this is R3 phi theta acting on V, at least for small angles. So this tells us that that this commutator L1, L2, well, by definition, that's going to be equal to L3, because what we found is that the commutator here was equal to a rotation in the third direction. So this is, of course, just the realization of the more general. We saw it, I think, in the when we discussed Hamiltonian mechanics, that the Poisson bracket between the angular momenta was given by Li Lj goes to epsilon ijk Lk. And this is the same thing, again, as pertains to your question. These structure constants for rotations in 3 dimensions, they are just these permutation symbols. Now, apart from these commutators, we have some additional relations among the elements. So, for example, you remember that in the discrete case we had the generators and we had some relations among them. In this case, we also have some relations for the generators themselves. For example, we know that for rotations, a rotation by 2 pi is the identity as well. So additional here is that r(i) to the 2 pi is the identity. Any questions?
Do you mind repeating what the connection between the Lie bracket and the Poisson bracket was?
So when we look at the symmetries in Hamilton mechanics, the Lie bracket is the commutator is the Poisson bracket, which is it has all it has all of the required properties. And in particular, we see here that in the case of rotations, it's actually the same. So the generator of rotations are the angular momenta.
Okay.
Now, I wrote down as an exercise here. We're not going to have time to do it online, but it can be good for you to do it as an exercise, since there are no exercise classes in this extended course to compute the in 2 dimensions, to compute the commutators between the generators of the 2-dimensional translations and rotations. So you can here compute as an exercise. Compute this pxl and pyl. I mean, if you look at px py, that is going to be 0 because translations commute with each other. And you can do it in a similar fashion to how I did these commutators for 3-dimensional rotations. So before the break, let's start discussing matrix groups. Now, we so far just have been essentially discussing formally what groups are, but matrices in general provide you with a very nice representation of groups. So, and that's because matrix multiplication inherently is associative. And if you remember, that was one of the requirements for a group operation. So matrix multiplication is associative. So it will automatically fulfill number 4 of the group theorems. So what we need to check in order to if we have a set of matrices is the other 3. So first of all, we need closure. So if we take a set of matrices, is the product of 2 matrices, again part of the set. The second is that we need to have an identity. And there is only one identity when it comes to matrix multiplications. So it means that the unit matrix that must belong to this set. And third is the inverse. So if A is in the set, then A inverse should be in the set too. So if we have a set of matrices that satisfy these 3 under matrix multiplication, then we have a matrix group. And if we look at the Lie algebra of matrix groups, then actually what we can do is that we can take this this exponentiation more seriously. Or more at face value, or as the matrix exponential. And this will lead to this commutator J1, J2 is then actually the matrix commutator. And also the elements of the Lie algebra will also be matrices. They will be a different set of matrices, but they will be matrices. And they will be considered a vector space instead of this group. So just before the break, to take a few examples of this. So if I take all n by n matrices, does this form a group? Well, we can check let's check the requirements. So closure, if we multiply 2 n by n matrices together, it's an n by n matrix. So it does satisfy 1. Identity, well, the identity matrix of n by n matrices is an n by n matrix. So 2 is also satisfied. However, in general, matrices are not invertible. So the set of all n by n matrices cannot form a group. This is not a matrix group. However, if we just remove all those matrices that are not invertible. So matrices that are invertible, or equivalently, the determinant of the matrix should be different from 0. This is going to form a group. And we can check that because well, n by n matrices. The first one is closure. So we know that if we take two matrices A and B, the determinant of the product is the product of the determinants. Right? And since both the determinant of A and the determinant of B are non-zero, the product is non-zero. So indeed, we have the closure property because the product of two invertible matrices is another invertible matrix. 2, identity. Well, this one is rather simple. So the determinant of the identity matrix is 1, and 1 is different from 0. So the identity is clearly invertible. And finally, 3 is that there should be an inverse. So we know that the determinant of A inverse, well, that's 1 over the determinant of A, which is non-zero if the determinant of A is 0. So the group of invertible n by n matrices, well, invertible n by n matrices form a group. So this group is called the general linear group. And we write it GL of n. So this GLN is the set of all invertible matrices of size n by n. So that's a group. And what's the Lie algebra of this group then? So what is the Lie algebra? Well, in order to find out what the Lie algebra is, we need to find out what kind of restriction on the generators we get from this condition. So if we write down the determinant of e to the theta j, we can use the relation that this is actually the same thing as the exponent of the trace of theta j, which since we have since the trace is linear, this is exponent of theta trace j. And this should be non-zero. But if we take the logarithm of both sides, well, the logarithm here, we have the exponent of something, and whatever, well, this is a real number, and the exponent of any real number is non-zero. So actually, this is true for any matrix J. So the Lie algebra is all n by n matrices. And the commutator is the matrix commutator. Let's just quickly go through another example and then have the break. So we'll still have a 15-minute break. But so the next example is called the orthonormal group. So we take n by n matrices that satisfy the following relation, so that A multiplied by the transpose of A is the identity. Or if you will, this is of course equivalent to saying that the inverse of A is its transpose. So real n by n matrices. So the question becomes, is this a group? And one of the things, again, let's look at the determinant here of this defining relation. So A is part of this group if this is true. That means that the determinant of A transpose must be equal to 1. But this is also equal to the determinant of A times the determinant of A transpose. But the matrix has the same determinant as its transpose, which means that the determinant of A squared is equal to 1, which means that the determinant of A is plus minus 1. So this is also the set of all real n by n matrices with determinant plus or minus 1. So first of all, closure. So the determinant of AB is again the determinant of A times the determinant of B, which if both the determinant of A and the determinant of B has magnitude 1, then that is also true for their product. So this is a plus minus 1. So A times B is also an element of the group. 2, identity. Same thing again. The determinant of the identity is 1, and that satisfies that it's either 1 or minus 1. And finally, the inverse. The inverse is that determinant of A transpose is equal to determinant of A, which is plus minus 1. So also the inverse is part of this group. So now we have shown that this orthonormal group is actually a group because it satisfies all of the group requirements. And we can look at the Lie algebra, which is, again, if we go back to this argument that we had here, this relation. If we do this for the orthonormal group, then we have that the determinant of e to the theta j is the exponent of theta trace j should be equal to 1. And well, this is just numbers now. So if we take the logarithm of this, we find that theta trace j should be equal to 0. And this is only true for all theta if the trace of j is equal to 0. So the matrices that form the Lie algebra of this orthonormal group are the matrices which have 0 trace. And this is called the orthonormal group, and the typical nomination for this is ON. We can also look at a subgroup of this, which is called SON, and that's just restricting the determinant to be plus 1. So removing all the matrices with determinant minus 1. Just during the break, I took the liberty of writing down an exercise. I mean, again, this is not something we will do here in the lecture, but it's something that might be good for your own understanding to check. So just as we saw at the end of the last hour, that the orthonormal group was a group, and that the general linear group was a group, we can do the same thing for a set of complex n by n matrices that are such that A multiplied by its own Hermitian conjugate is equal to the identity. And this group is called the unitary group. And if we restrict that group to those matrices which have determinant equal to 1, rather than having the absolute value of the determinant equal to 1, we get the special unitary group, SUN. And the exercise is to show that those are groups, so that they satisfy the group axioms and to deduce what their Lie algebras are, just as we deduced the Lie algebras of GLN and ON. You don't need to write this down. I'm going to put the lecture notes up later today on Canvas, and I will also put the video up so you will have access to this later today. With that being said, let's move from continuous groups to group representations. So representations will be the topic essentially for the rest of today and for the rest of my lecture series at least. Next time we will look at how we can use representations to draw certain conclusions regarding physical systems. But today we're just going to look at what representations are and look a bit at some particular representations that might be useful later on. So, given a vector space, V and a group G. So this is going to be the definition of what a representation is. So a representation of G on V is a homomorphism from G to linear operators on V. So it's relatively easy to check that the set of linear operators on a vector space are going to form a group by themselves, or are the invertible linear operators on V. So what we're saying is that for A in the group G, we are looking at the map where A maps to rho of A, where rho of A is a linear operator on V, such that rho of A, rho of B, that's rho of A times B. So that's the requirement of being a homomorphism. And so this is the definition of representation. And we also say that the action of G on V, defined by this representation, is how this representation acts on the vector space. Is given by rho of A acting on V, where V is a vector in V. So just to try an example of that, we're going to first look at the kind of the most intuitive representation that we can have. So we're going to have rotations in 2 dimensions. So in general, a rotation by theta, if we act on E1, we get cosine theta E1 plus sine theta E2, and if we act on E2, we get something similar. We get minus sine theta E1 plus cosine theta E2. Now, if I write now a general vector V, which is V1 E1 plus V2 E2, if I represent this with the column matrix V1 V2, this means that V under these rotations map to cosine theta minus sine theta, cosine theta, multiplying V, right? And we see here that this here, well, first of all, what we have here is a two-dimensional vector space V. This is, all the vectors are going to be in a two-dimensional vector space here. So this is R2. And this vector is also in R2. And what is here is a linear operator on R2. So it's a 2x2 matrix, which maps a vector in R2 to R2. And if we take the determinant of this, so if we call this A, we find that the determinant of A is 1, because it's cosine squared plus sine squared. And if we go back to the end of the last hour, then we see that this is actually the definition of A being an element of SO2. So in general, we're going to find that rotations, pure rotations, in n dimensions is going to be isomorphic to SON. So this is actually now a map from the more abstract group of rotations in 2 dimensions to the matrix group SO2. So this A here is actually the representation of the 2-dimensional rotation by theta. So of course, when we, as long as we have a finite dimensional representation, we can always represent it by an n by n matrix. So for finite representations or finite dimensional representations, we can say that the representation is a map from well, in general, the more abstract group, but can be any group, to n by n matrices, or some subgroup of n by n matrices. Just to mention another example, which you might encounter, that's called the trivial representations. So regardless of G and V, we can always map all of the elements of G to the identity on V. So rho of A is equal to the identity. This is always going to be a representation, and it's called a trivial representation. If we compare to the rotations in 2 dimensions that we just discussed, when rotations naturally act on a vector space, sorry, when a group naturally acts on a vector space, such as, rotations are defined as rotations of a 2-dimensional vector in this case. So when we take like how it naturally acts on that vector space, we talk about the fundamental representation. So this here is the fundamental representation. Of two-dimensional rotations. Okay. Any questions so far? Okay, so what I want to do now is to go through a couple of representations that we can construct if we already have other representations. And they're going to be quite important for the discussion that we're going to have next time. So the first one is the tensor product representation. That is to say that if we have two representations of G, so given representations of G, so row 1 and row 2 acting on V1 and V2 respectively, then we can construct a new representation, which is called the tensor product representation, which is a representation on the product space of V1 and V2. So the tensor product representation, which I'm going to write row 1 tensor product 2, is defined by defining the action on tensor products of vectors in V1 and V2. So sort of the following. So let Vi be an element of Vi, then V1 tensor product V2, that's an element of the tensor product space V1, V2. And I'm going to define the action of this representation on this tensor product space as follows. So if I take row 1, 2 here, and I act on, and I represent some group element A, and I act on this V1 tensor product V2, I define this to be the tensor product of the representations acting on the individual V1s and V2. So this is row 1A acting on V1, and its tensor product with row 2 of A acting on V2. Now, this is always going to be a representation, because what we want from a representation is that it's a linear operator, and in this case on this tensor product space, and that we have a homomorphism. So we can check that this tensor product representation actually is a homomorphism. So that means that we need to check now that row 1, 2 of AB, that should be the same thing as row 1, 2 of A times row 1, 2 of B. So we can just do this through the definition here. So if we take row 1, 2 of AB and we act on V1, V2, just using this definition here, we find that this is row 1 of AB acting on V1, and then the tensor product with row 2 of AB acting on V2. But we can now use that row 1 and row 2 by themselves are representations. So this means that here we have row 1A, row 1B acting on V1, and the tensor product with row 2 of A and row 2 of B acting on V2. And now we use the definition in the reverse direction, which gives us that this is row 1 of A, sorry, row 1, 2 of A, multiplied by row 2 of B, row 1 of B, sorry, V1, tensor product with row 2 of B, V2, and using the definition again in the reverse direction, we find row 1, 2A, row 1, 2B, acting on V1, V2. So indeed, this definition of the action of the of this representation on the tensor product space means that it's actually a representation, because it satisfies that row 1, 2, AB is the same thing as representing B and A separately. Now there is of course nothing prohibiting you from having V1 being the same as V2. In that case, it will just be the tensor product of a vector space with itself. Questions on that? So let's take an example. So what we're going to look at is rank 2 tensor representation of rotations. So rotations in general, they transform vectors as Vi goes to Aij, Vj, right? And these Aij's may be considered as the components of an n by n matrix. In this case time, if we look at 2 dimensions, 2 by 2 matrix, which we saw here before. So this 2 by 2 matrix, for example. What we're going to look at now is the tensor product representation. So we're doing a tensor product of 2-dimensional vectors. So rank 2 tensors transform, rather their components transform as Tij. Well, since it's the tensor product, let me write the indices upstairs. But Tij, it goes to Aik, Ajl, Tkl, right? So what we have in front here now are the components of a 4 by 4 matrix, essentially.
Can I ask a question?
Yeah, sure.
TKL, why aren't the indices, under indices?
I wrote all of the indices here upstairs, right?
But if we transform them.
So the transformation, this is not a lowering of the indices. This is just a rotation.
I understand. Thank you.
And that's why also I have a 1 index up and 1 index down in the transformation coefficients.
Yeah, I understand. Thank you.
So this is the transformation rule. And if you look at it, the tensor product space here, since we're looking at 2-dimensional vectors, the rank 2 tensors form a 4-dimensional vector space because there are 4 possibilities of choosing K and L. We can choose. So let's write those down. So K and L, or more general, well, let's write I and J instead. So I and J, the possibilities we have is 1, 1, 1, 2, 2, 1, and 2, 2. And we can just number those. So we can introduce some other index I, and we call those 1, 2, 3, and 4. So if we do that, we can write down we can write down this tensor as a vector, essentially T11, T12, T21, T22, and we can write down this transformation as this T21 and T22. And then we have some matrix here in front that its elements is going to be A11, A11, and then it's going to be let's see, A12, A11, A13, A11, and so on and so forth. So you can actually write down all of those components. But the main thing is here that we have a matrix here, which is a 4 by 4 matrix. And that matrix is the representation of rotations on the tensor product space. Okay, so that's the tensor product representation. The next representation is the direct sum. So when we have a vector space, or when we have two vector spaces, just like for the tensor product representations, when we have two vector spaces, we can make their tensor product, which is if we have an n-dimensional and an m-dimensional vector space, their tensor product will be n times m dimensional. But we can also make their direct sum. So given two vector spaces, v1 and v2, we can say that their direct sum, which I'm going to write v1 o plus v2, is a new vector space. Which is just all doublets of v1, v2. And the sum in this vector space is given by, if you have v1, v2 plus u1, u2 is just the sum of the individual vectors. Like that. This is also a vector space on which we can create a representation if we have representations on v1 and v2. So given representations of some group G on v1 and v2, let's call them ρ1 and ρ2, just as before, we can define the action of the direct sum representation as follows. So we take ρ1 and now plus O plus 2, A acting on this type of element, v1, v2. We're going to define this as the individual representations ρ1 and ρ2 acting on the separate elements. So this would be ρ1, A acting on v1, ρ2, A acting on v2. And showing that this actually is a representation goes much in the same way as we showed that the tensor product representation was a representation. Note that the difference here is that this space here is n1 plus n2 dimensional. Whereas in the tensor product case, here, this space is n1 times n2 dimensional. So in general, they are going to be different vector spaces. And they're going to be different representations. Even if kind of the definition of these representations kind of remind of each other by the fact that we're just acting on the individual elements here, just as we did in the tensor product case, but they are actually different representations. So I will. There is an example of this in the chapter on group theory in my book, where I, in particular, I mean, in the case of two-dimensional rotations that we saw before here, this matrix, all of the matrix elements here are generally going to be non-zero. But if you look at the same thing here, so the example here is R2 plus R2 for rotations in 2 dimensions, then what this is going to give you is a matrix which is essentially cosine theta minus sine theta, and then sine theta cosine theta in the upper left. Then you're going to have zeros on the off diagonals, and you're going to have the same repetition here: cosine theta minus sine theta, and sine theta cosine theta. So this representation is actually quite different from the tensor product representation. So we have 15 minutes left. What I want to spend those 15 minutes on is what is called reducible representations. And this is going to be rather important next time, because next time we will get to irreducible representations, which is of course nothing else than if a representation is not reducible, it's going to be irreducible, and we're going to see the connection to physics quite strongly there. But in order to discuss it, we first need to go through what a reducible representation is. So 2 representations. Rho and rho prime. First of all, I want to define what equivalence means in terms of representations. On V, they are said to be equivalent if there is an invertible linear operator, which I will call U, on V, such that rho of A is equal to U rho prime of A U inverse for all A in the group. Now, we say that a representation is reducible the keyword being reducible here, if it is equivalent to a representation on the following form. So rho, we call it rho d of A, should be represented as rho 1 of A, then some sigma of A, rho 2 of A, and then a 0. So what this means is that if we have here a subspace, so in particular here, if we have a vector that looks like this, 0, v, then this is going to map to a vector that is, no, sorry, in the other way around, v0. That's going to map to a vector. If we first multiply here, we get rho 1 of A acting on V. And if we multiply here, we get 0, right? So it's mapping vectors of this form to vectors of the same form, which means that there's an invariant subspace. So the subspace of vectors that just have the components in the, like, let's say M first components. In other words, if there is an invariant subspace. Of V under the action of rho. Now, if the group is finite, then we can always write this. We can always find the basis of the vector space such that such as sigma is equal to 0, assuming that the representation is indeed reducible. So that would give then that this rho d of A would be rho 1 of A, 0, 0, rho 2 of A. And note here that these are block matrices. So this in general might be an n by n matrix, and this might be an m by n matrix. So this means that we have separate representations rho 1 and rho 2 acting on the subspaces. V1 and V2. So our original space V here would be the direct sum of V1 and V2. Questions on that? We're going to see an example. Sure, it's the next thing we will do. So hopefully this will become clear with the example. So the example I will take is the representation of 2D rotations, or SO2, on R3. So I'm going to represent two-dimensional rotations in 3 dimensions. So we can do that by representing those two-dimensional rotations as rotations about a particular axis. So let's represent rotations by theta, by an angle theta, as rotations by theta around the E3 axis. So the Z axis. Now, my matrix rotations, my matrix representation of rotations in 3 dimensions is SO3. So this representation will be a subgroup of SO3. So the way I do this is that I represent this two-dimensional rotation, rho r, by cosine theta minus sine theta, cosine theta, 0, 0, 0, 0, 1. So this is a rotation about the z-axis in 3 dimensions. And it's how I represent my two-dimensional rotation in 3 dimensions. And you can see now this is exactly on the form that we discussed. This is exactly on this form. It's just that rho 1 here is a 2 by 2 block, and rho 2 is a 1 by 1 block. So what does this mean? Well, if we look at the invariant subspaces here, what are those spaces that we're acting on? So V1 in this case is the two-dimensional space spanned by E1 and E2, while V2 is the 1D space spanned by E3. Row 1 is the fundamental representation of R2. So we are just having the fundamental representation of R2 in the two-dimensional subspace of R3. And then we're having row 2 is the trivial representation of R2. We see that because all of the elements are represented by a 1 in the third direction. So looking at that, let's just draw something here. So if we have the different directions here, so this is E3, this is E1, and this is E2. If we have a general vector here, so this is my vector V, then I can decompose this into the part that belongs to V1, which is the projection into the E1, E2 plane. So this is going to be this vector. And in that place, in that plane, I'm representing my rotations by rotation in that plane. So this is going to rotate to some new vector by an angle theta. Whereas in the third direction, the component in V2, well, that's what is orthogonal to the E1, E2 plane. So let's take some other color. Let's take purple. So that's here. The projection onto the E3 axis. And under this rotation in 3 dimensions, which represent the 2-dimensional rotation, this which I can call the orthogonal, the component in the E3 direction does not change, which means that it transforms under the trivial representation of rotations. So the full vector, of course, if we look at it just transforms as a rotation by an angle theta around the E3 axis.